Check. Okay, yeah, go ahead.
Okay, hello everyone.
We cannot see you.
Okay, I should come in the picture. Okay, hello everyone. Welcome to Safari Live Seminar. We are again resuming back our Safari Live Seminar, and we will be having a couple of interesting talks coming up in today also and in upcoming weeks. And today we have Manos Frouzakis. Manos is a research assistant at Safari and holds a master's degree in electrical and computer engineering from ETH Zurich. His research focuses on PIM, processing in memory, and in-storage computing for alleviating data movement bottlenecks in modern computer architectures. Today, he will be presenting his work PIMDAL, mitigating the memory bottleneck in data analytics using a real processing in memory system. With that, let's get started.
Okay, so I can start immediately with the executive summary for this presentation. So first, the problem. The performance of like database operators and data analytics in general is limited by the access to off-chip memory in current processor-centric architectures. And the motivation for this work is basically that since processing memory architectures move computation to where the data resides, namely the memory, we want to evaluate if we can use a real processing in memory system to accelerate such analytical query processing. And the challenge in this is that current database implementations are tailored to the processor-centric architectures, which cannot be straightforwardly ported to PIM architectures, since the hardware characteristics of these systems are entirely different. And so the goal of this work is to create an implementation of TPCH queries, which is a widely used benchmark to implement this on the optimum PIM system while achieving a optimal performance in order to optimally be able to characterize processing in memory systems for analytical query processing. And the key results that we got from this characterization is that PIM can outperform the CPU in 4 out of 5 TPCH queries by about 3.9x on average. And it can outperform in the GPU on 2 of those queries that require less communication than the other ones. I will come to this later. So here is the outline of my talk. So first on the background and goal. So database management systems were developed in the late 1950s, which was even before the invention of the microprocessor. So basically, even before people knew how computer systems and architectures are going to look like, they knew that they want to use this for data processing and management. And they basically evolved together in parallel with computer architectures. For example, when the main memory sizes started getting larger and larger in computer architectures, they started developing main memory databases, which keep all the data in the RAM. And through this, they can avoid the overhead in terms of performance and energy compared to having to move all the data from storage. However, these in-memory databases still suffer from data movement bottlenecks due to the design of the current computer architectures, because they still need to fetch data from off-chip main memory to a central processor unit, which comes with significant overheads. So now, what are like databases and database operators? So a relational database, in the simplest term, is just a collection of different tables where we store data. And each data point that we want to store is a row in such a table. And a row is like a tuple with different entries that each belong to a set of data. And this is also why we often call like these operators like set algebras. And a database operator now performs operations on either like rows or columns of either one or multiple tables. And these are the 4 database operators we consider in the PIMDAL, which is first selection, which filters tuples based on a predicate of a column. So in terms of like, let's say, data analytics for business, if we have like different products, we can filter them based on a price to find like all products that are cheaper than a predefined price. Then aggregation. So to aggregation, we refer to grouping with aggregation, where we basically take like one column, let's say like product categories, and then we want to like group all items that we have, like the products, into these categories, so that we then can aggregate the other columns that we have. For example, we can find like the total price of all products in like one category. Then ordering is like straightforward. We just want to order our tuples based on some columns. For example, we want to like order by price. And then finally, join. Since we often don't want to store all the information in one table, especially if we would have a lot of duplicate information, we often store them in different tables. So for example, if in one table we have like the products and in the other the manufacturers, and then if we want to like combine these 2 tables together, we use the join operator, which joins them based on like the manufacturer key, for example, so that we can then do further processing on like the joint tables. So now the big issue of database operators is that they are bound by memory accesses in current systems. So to determine this, we want to to calculate the roofline model of the DB operators. And we performed this on an Intel Xeon CPU with DDR4 DRAM. And so basically this is what the roofline model looks like. We have the horizontal lines, which show that the performance is limited by the arithmetic performance of the CPU. So the lower line is like the standard integer operation, scalar integer operations. And the upper line is the more advanced vectorized integer operations. And the slanted lines are the different memory bandwidths that we have in our system. And so basically, if an operation is bottlenecked by or memory bound, it means that it's going to be like in this region. And in the x-axis, we have the arithmetic intensity, how many operations we do on a byte of data. And on the y-axis is the arithmetic performance that we reach. And so first, about selection, we can see that selection is bound by the main memory, and it has a very regular accesses, which means that it cannot really take advantage of the cache, which is the case for aggregation, which you can see it has very similar arithmetic intensity than like selection, but because we can perform like some operations, some of the writes on the cache, we have a higher arithmetic performance in the end. Then ordering is a bit more memory bound than these previous two operations, and it's also, so it means it has even lower arithmetic intensity, and it can also not really take advantage of the cache to improve its performance. And then finally we have join, which is the most least arithmetic intense operators of all four. And join, it has like some slight like cache utilization, but not really ideal also.
Can we ask questions now?
Yes.
Or
Yeah, of course. No,
Okay.
of course.
So I'm curious if you can generalize these observations across, like, whatever behavior you see for selection in this analysis. Is it true for like all selection operations across all source of relational databases out there in the world? Like if your database structure changes, for example, for different architectures, does it hold, like, can you generalize this way?
For selection, you can, like, selection is, it's pretty simple, so it's gonna be more or less the same. Oh yeah, overall, I mean, like probably like selection, ordering, and join, they don't change much depending on your use case. What can probably change is aggregation. If you have like very complex aggregation function, it might be like less memory bound.
Oh, I see.
But yeah, overall, the other three I think is pretty generalizable like this.
Thanks.
So yeah, so what you can get from this is that the performance of our four database operators is bottlenecked by the accesses to the main memory in current computer. So now to the PIM system that we consider in this work, which is the UpMem PIM system. So here is a figure of how the UpMem PIM system looks. And how you can see what it tries to do is like extending the standard DDR4 DIMMs with DIMMs that are equipped with PIM cores or DPUs on the UpMem PIM system that can be used to do processing inside the main memory. And these PIM cores can access the internal DRAM with a very high bandwidth. And they are simple, multi-threaded in-order RISC-like cores. And they can execute their code independently, like each thread can execute completely different code, which is more flexible than other systems like GPUs, for example. And they, instead of using a cache like in standard computer architecture, they use a stretchpad memory, where the transfers from DRAM to stretchpad have to be explicitly managed by the programmer, which I will get further into a bit later. And one key drawback of this UpMem PIM architecture currently is that the inter-PIM core communication needs to happen over the host. So these PIM cores that you can see here cannot directly communicate with each other. They need to first go to the host main memory, and then from there the data can be moved to other PIM chips. So now to the challenges and limitations of the optimum PIM system. So if we just implement our database operators like we do on a standard system without taking into the consideration the characteristics of the optimum system, this can lead to very subpar performance for three main reasons, which I will explain now, which is the data movement inside in the PIM code must be explicitly managed by the programmers. It's not like the cache in current computer architectures, and if we don't do this optimally, this will degrade the performance of the code, as I will also explain more depth later. And some database operators can require multiplication or division, which is very slow on the optimum system since it lacks the dedicated hardware unit to perform these operations. And some database operators can require redistribution of data between like PIM cores, which requires communication over the host, which also needs to be managed in an efficient way. So now to the goal of this work. So the idea is to create a high performance implementation that optimally addresses the limitations of the optimum PIM system of the TPCH benchmark, which is a benchmark for comparing commercial database management systems to evaluate the potential for PIM for analytical query processing. So for this, we implement the database operators on a real-world PIM system while addressing the challenges that we previously mentioned. And we want to discover the strengths and the limitation of current memory-centric architectures for analytical query processing. And to this end, we propose PIMDAL, which is a library for analytical query processing on the optimum system that supports these TPCH queries. So now I'm coming to PIMDAL and how we implemented it. So we want to start by first deriving like two main design principles from like previous characterization of the optimum system. So the latency of the data transfers between DRAM and scratchpad memory has like this form of a constant term and a term that depends on the size of the transfer. And these terms are not really fixed. They depend on like if you read or write data. But overall, what you can say is that we want to use as big continuous DMA transfers as possible in order to better amortize this constant latency term in the data transfer. And the second principle is that since the pipeline needs as many PIM threads as possible for optimal performance, and the full occupancy is usually achieved at about 11 working threads. The principle is to use at least 11 PIM threads. And the challenge in this whole thing is that since the scratchpad memory is shared by all the threads and our transfer size depends on how big our buffer is, there can actually be an issue if you have like too many threads that try to contend for this scratchpad memory, which would lead to very small buffers and with that small data set. So we need to find a way to also balance these two design principles. So now to the structure of PIMDAL. So PIMDAL consists of a PIM and a host component. And the task of the host component is to basically feed the PIM system with data and provide communication capability between PIM cores. And for this, it can load like data from disk, which we will need for our benchmark later, and transfer data between host and PIM system. And it can also redistribute data between PIM cores. And the PIM component implements the 4 database operators: selection, aggregation, ordering, and join. And it operates on data which is stored in the PIM DRAM banks in column store format, which is that the columns of each tables are stored contiguously in memory, which simplifies like sum operation. Okay, so now further into the PIM component of PIMDAL, there are like 2 important algorithms to support for database operators, which are sorting and hashing, and they are mainly used in aggregation and join. So in aggregation, we want to group equal elements together. So one way to do this is to sort these elements, which then means that the equal elements are just stored contiguously, and we can iterate simply through them and aggregate the columns that we want to aggregate. And it can also be implemented by hashing, by like mapping equal elements that need to be grouped together to the same entry in a hash table, where we then can aggregate also the columns we want to aggregate. And for join, we can implement it using sort merge join, which basically just sorts the 2 tables so that we can then iterate through the keys and match them up easily if they are equal. And the hash join works by storing like the inner relation or one inner table in a like usually the smaller table in a hash table, which we then can probe with the keys from like the outer relation to see if they match and if we can join them. So first, to like sorting and a short overview of the challenges we faced when implementing sorting on the UpMem system. So quicksort is one of the most common sorting algorithms used today, and it is well suited for the UpMem PIM system due to its characteristics. But how it works is that you repeatedly partition an array into 2 partitions, so that like, the bigger elements in the array are stored in like 1 partition and the smaller elements are stored in the other partition. And the issue is with efficiently parallelizing quicksort. So in theory, the threads could all work independently on partitions. But if when we start off, we only have like 1 partition, so we only can work with 1 thread. Then in the next iteration, we get 2 partitions, which is still not enough to saturate our PIM system, then 4 and so on. And we found this to be a major issue. So the solution for this was to first just split up our array into different parts, and then each thread can independently partition his own part into as many partitions as we need. And then we can calculate the prefix sum over all the partition sizes in order to then get an output location in an output array, where then at the end we will have like different partitions that can now be processed by the threads in parallel independently. So now to hashing. So we have 2 applications for hashing in PIMDAL, which is first to insert the elements into a hash table, which you can probe fast, and to partition the elements for easier processing. For example, if you want our hash table to fit inside the scratchpad memory. So the issue with hashing is that hash functions often use like complex operations, like the one you can see here, where A and P are constants, which are usually picked to be prime numbers in order to achieve like good performance, and M is the hash table size. And theoretically, it could be possible to find these values A and P that perform fast on the Upman system, since the implementation of like multiplication and division is a software algorithm, which depends on the complexity of the values that you use. But we found that it's not possible to find like fast performing values that also make good hash functions. So in the end, we opted for using like shift and XOR based hash functions, which can be performed much better on the Upman PIM system. So now to the host part, and one very important optimization that we had to make in the host component of the PIMDAL. So if we just redistribute our data naive, so assume that we have each PIM core has like its data in partitions where it wants to send each of those partitions to another PIM core, like basically an all-to-all transfer. If you want to do this, if we do this naively, we just copy all the data from the PIM memory to the host using parallel transfers first. And the issue with these parallel transfers is that they can only transfer a contiguous memory sections. So if you want to transfer data using this parallel transfer, we first need to make sure that they are stored contiguously inside the host's DRAM, so that we then can transfer them back to the PIM system. And so, yeah, what we do is just reorder them on the host system, which kind of defeats the purpose of using PIM. And then we use parallel transfer to copy the data back to the PIM memory. And here is an example timeline of the execution of this process on the PIM system. Like the bars you see is where the PIM system is active, and the white spaces in between is where the PIM system is waiting idly for the host system to perform some operation. And there are first like two key reasons for this idle time, which is allocating space on the host to store the transferred data. And then the second main part where it's idle is where we are reordering the data on the host system. So one optimization we can do is we can use scatter transfers, which can copy disjoint data chunks to different PIM cores, which avoids the reordering that we mentioned before. This now allows us, instead of copying data, reordering and copying back, just copying the data and then directly copying it back in the order that we desire. And each partition can be directly transferred with this approach to the destination approach with a destination PIM core without reorder. So here is how our example timeline now looks like without this reordering step. You can see that in the middle, the time we need for reordering has been greatly reduced, and we have already saved some execution time. But as you saw, there is still a big issue with, yes?
So in the previous slide, like still we have, so it depends on the disjoint, the data that we are doing the scatter transfer. It also depends how contiguous that disjoint data is, right?
Yeah, I mean, it kind of depends on it. Like if it's very small, like parts, then it theoretically is not gonna have as good performance. But in practice, we didn't really find that to be an issue.
So the data is always present in a contiguous manner, is it what you are saying? Like
No.
already in some huge, not in a contiguous, but in some huge chunks in this disjoint.
Yeah, like the chunks should have ideally some certain size, probably like related to the like virtual memory page size. But yeah, overall we didn't find this to be an issue if the data is like too small to be efficiently transferred using scatter transfer. So yeah, the second key issue that you saw was that the allocation time is a very huge overhead. So basically, like using the standard POSIX allocators like malloc took a very long time for the data sizes that we had. And for this reason, one framework that tries to provide an efficient memory format for data analytics, which is Apache Arrow, uses a custom allocator, which is the JE malloc allocators, that basically uses its own custom memory pool that is faster to allocate data from than using the standard malloc allocator. But however, I'm not really sure why it was so much faster what we observed, because from what is in the documentation of the JE malloc allocator, we cannot really expect such a huge speed up that we observe in our application. And by using Apache Arrow, as UpMem also suggests, we can significantly reduce the allocation time of our application, which now looks like this, the timeline. So it basically has vanished this overhead of allocating data. However, we still see that there are like some small inefficiencies where the system is idle. And this is because it's like different PIM ranks have to all wait until all have finished to continue with execution. So to avoid this, the UpMem SDK also enables us to do everything asynchronously, which means that transfers and execution can happen asynchronously for different PIM ranks. So they don't have to wait for all other PIM ranks to wait until they can continue with execution. And this means that if we transfer our data to different PIM cores, they don't necessarily need to happen at the same time anymore. And the effective bandwidth of our system is improved by this. And by using all the optimizations that we have now presented, we can reduce the overall execution time by about 6x, which now looks like this. So as you can see here, the PIM cores now, after transferring the data, can immediately start executing, which then means that the overall like time it takes for execution is greatly reduced. Yes.
So from a really naive point of view, and really high level, so you address the data movement related performance issues by doing this. And still, when we look at the fraction of the PIM execution, it's really tiny compared to the transfer, right? And I'm not accusing, like, it's your fault, of course, but what do you think, like, we can do to further reduce this transfer time and make like the execution most of it basically?
I
Is it
will
because
also,
of Upman's design or?
yeah, basically it's a limitation of the Upman system. I will also get or explain this in more detail in the evaluation, and also in the end we can like have a discussion on this, because it's also a key area of research currently in optimizing like data transfers between like PIM cores or PIM processing elements.
Mhm. But why do we need to do this PIM to host, host to PIM transfer all the time? I missed that part, I guess.
Because we don't have like direct PIM to PIM communication, it all needs to go through the host. Like they only have like a direct channel
It's
to
for
the.
the communication between PIM cores.
Yes.
Okay.
But yeah, we'll discuss this in a lot more detail.
Okay.
Can I ask one
Yeah.
thing? In this slide, like once you do asynchronously and go, like when you have PIM rank as 4, like most of the time Upmem system is busy doing something, right? Either it's a data transfer or it's a computation execution. So is there anything like on top of this, is there an improvement that we can do from this data transfer side of of these databases so that we can improve further? Or is it the max that we can achieve? That Upmem is busy, but we can still see, okay, the performance is limited by the transfers, but Upmem is busy in doing something, right?
Yeah, I don't think there is like much to be optimized here for from the algorithm side. Like I tried also coming up with more like maybe complex communicate or clever communication patterns that can hide kind of this overhead of computation and transfers. But one key issue is also that the PIM cores cannot concurrently compute and transfer data. So you're always gonna be limited in the end by the data transfers. I mean, this would maybe be also further optimization of the system. If you can do like computation and transfers together, then you could hide some of the communication overhead, but currently this is not possible.
And how frequently these PIM units needs to communicate with each other in these sort of operators?
It depends on the operators. Usually, I mean, it's most once usually, but I will also explain this in more detail.
Okay.
Are there any other questions right now?
I had one, but it was some earlier slide. So
I mean,
but it's
know
okay. I can just read from here. I took notes. So in the very beginning, when we were talking about the principles, you talk about doing data transfer over DMA and in bulk.
Yes.
So does it assume that whatever data you're working on PIM is like exclusive for those PIM units, PIM cores? Like if we imagine a case, and maybe it's not the case for your workload, but if you imagine a case where the same data is also used by the CPU core and there are some coherence issues, and magically we solve the coherency by applying some like efficient protocol, but now we need to do some like data transfers of small amounts of data. Does it bring like new challenges to the problem you're tackling here?
I mean, yes, it would be, I think overall it would be very beneficial for this problem if you like would change the whole approach to work on like consistency based approach instead of needing like this explicit transfers. But Yeah, I mean, it would also bring like it would change the whole implementation as it currently is. Like, this is one of the, I mean, this is what that kind of PIMDAL does, is address like this current use case, and it would not really be flexible to change it to a different like PIM concept or architecture.
Okay. Thanks.
So now to the experiments and methodology of our work. So first, we want to do a series of micro benchmarks which measure the performance of just the standalone operators and compare to the CPU and GPU in order to be able to get some insight on what the key factor is in the performance of database operators. And for this, we measure just the kernel execution time on the PIM system, the IPC of our in-order pipeline to see how well our compute units are actually utilized in the system, and a weak and strong scaling analysis of the whole end-to-end execution time, which includes all the data transfer from like host to PIM system. And in the weak scaling analysis, we just basically increase the number of PIM cores that we use, and together with this, the problem size or data size, in order to see how well the problem scales up on the PIM system. And in the strong scaling analysis, we just keep the problem size constant and increase the number of PIM cores that we use in order to measure how well the problem can be sped up by using more resources. And the main goal of our micro benchmarks is to gain insights on what limits the performance of our database operators in order to then later use these insights for implementing our queries. And we compare this database operator implementation also to CPU and GPU reference implementation, which is one like a custom implementation, which is based on Apache Arrow, which I previously mentioned, which is a data format for analytical, for data analytics that tries to tackle data analytics on conventional systems like CPUs, but from a more memory-centric approach. And they also implement like some database operators. However, the issue was that we could not really profile this in depth on the CPU, like we wouldn't get good results. So we implemented like these operators from scratch and making sure that the performance stays the same. And then we also compare to the GPU using the QDF library, which implements like databases and data analytics on NVIDIA GPUs. Then to our TPCH query experiment. So the TPCH benchmark is widely used for comparing like different commercial databases, and a lot of database companies actually use this to benchmark their systems. And it's a suite of what they say are so-called business-oriented ad hoc queries, where they try to gain like insight from data used in like sales data and other data that is used by a business. And we use 5 queries from this TPCH benchmark that do not need variable length data types, which would be a major challenge to implement on the UpMem PIM system. So we just chose ones that do not need this. And these 5 queries include a combination of all the database operators that we have implemented. And all of them require addition, while 4 of them require multiplication. which allows us to also measure how big the influence of the arithmetic operations will be on the PIM performance for these TPCH curves. And again, we have a reference implementations, which is one pi arrow on the CPU, which depends on the Apache arrow, and QDF again on the GPU. And the system configurations we consider, you can see here, they're like basic characteristics. One system is like the Atman PIM system with 2048 DPUs, then an Intel Xeon CPU and an NVIDIA A6000 GPU. So now to our evaluation and the insights we gained from this. So first, just a short overview over like the different operator implementation. And yeah, to get like back to the question on what operators require like data redistribution. So we can kind of group our operators into like simpler operators, which are like selection and aggregation, and ordering and join, which are the ones that need to redistribute the data between PIM cores. And so now first selection performance, which is maybe the least interesting. So we can see that the throughput increases like fast with increasing number of threads up until like 11 threads, which is when our pipeline is basically saturated. And then afterwards, you have like some small increase, which is because we can hide some memory stalls in our execution. And the IPC basically mirrors our increase in performance, which suggests that our resources are well utilized in the PIM system, since the more busy the pipeline is, the higher the throughput gets, and we don't have like unnecessary execution. So now to aggregation. So for aggregation, we want to compare the performance of our sorting-based and our hashing-based implementations. And we do this for a different number of unique elements or group, which means that the number of unique elements will correspond to how many groups we will have in the end, which has a big impact on the performance, as we will show. So first, for like sort aggregation, we can see that it's relatively inefficient for if you have very few elements, which is because when we do like the partitioning we showed in the like sorting implementation, this is very inefficient if we don't have enough elements. But after like some amount of like groups, we see that the sorting time just remains constant. And so for hash aggregation, the performance for few elements is a lot faster, since it doesn't have to do this unnecessary partitioning. However, since we don't partition the data, it also means that the execution time increases the more output elements we have, because they cannot fit into scratchpad memory anymore. And we need to repeat this aggregation step multiple times to process all the elements. And you can see like the limit where like the elements stop fitting inside the scratchpad memories, where the performance of hash aggregation starts to degrade. So the key takeaway we have from this is that the scratchpad memory or cache utilization still plays a role in the performance of PIM architecture, as it does on the conventional architectures, as the example of hash and sort-based aggregation shows. And since there are works that try to address this issue on conventional architectures, there is also room for improvement here, potentially, to improve the performance of aggregation on PIM systems. So now to ordering. So we can see that the IPC and the throughput increase basically just equivalently, which tells us that sorting is a very good fit for PIM systems and can utilize the resources we have in PIM system very well, which is in line with our theoretical expectations, since sorting has a lot of memory accesses, low arithmetic intensity, and simple arithmetic operations like just simple comparison of elements. So it seems like this is basically the ideal use case for current PIM systems. So now to join. So two commonly used join algorithms currently are hash and sort merge join. However, in the general use case, where overall, on conventional systems, we basically only use hash join since it achieves significantly better performance. However, what is surprising from our results on the PIM system is that sort merge join can outperform hash join. And this tells us that what we currently know about algorithm performance and what algorithms are better does not necessarily translate to PIM systems. And to explain this a bit better, we will do a bit of a deep dive on the performance of hash compared to sort partitioning, which is basically equivalent to the whole performance of sort merge join versus hash join. So here is the comparison of throughput and IPC of sort versus hash partitioning. And we can immediately see that sort partitioning is faster and, according to the IPC, also more efficient. Like the IPC increases almost uniformly for sort, while for hash partitioning it is pretty limited after some time. So the issue is that hash partitioning has a considerably higher arithmetic intensity than sort partitioning, which required us to take a different implementation approach than what we did for sort partition. So our implementation of hash partitioning relies on the radix cluster algorithm, which can improve the performance of partitioning. And I will now do a bit of a detour to explain this algorithm and explain why exactly the performance on PIM system is the way it is. So this radix cluster algorithm is implemented on CPU-based system to improve the performance of hash partitioning there. And how it works is, instead of partitioning the data in one go into all buckets, we use multiple iteration of sub-partitioning the data. So for example, instead of partitioning our data directly into 256 buckets, we can first partition it into 16 buckets and then take a second pass on each of these buckets and partition it into 16 further partitions. And the reason why we do this on conventional systems is to improve the usage of the TLB in virtual memory. Since if we have many partitions, we would have a lot of page table accesses that don't go to the TLB, but go to main memory, which would drastically reduce the performance of partitioning. So usually I think we have like TLB size of 16 in current processor, which means that ideally the number of partitions we want to do in each iteration is 16. On the UpMem system, on the other side, we don't have virtual memory, so we don't really care about TLB. But what we care about on UpMem is that the DRAM transfer sizes are big. And if you have a lot of small partitions, it will take a lot time to just transfer the data, as we explained for our design principle. So in the end, what you have is that hash partitioning performance using this radix cluster algorithm will be a trade-off between the number of iterations that you are going to do to partition and the duration of each iteration. So if you have a lot of iterations, but they are very short, it can be faster than having less iterations that each take very long. And this key point is now crucial to understand the performance of hash and sort partitioning on the UpMem system. So if we now want to compare the performance, the same observations that we have for like hash partitioning using the radix algorithm is that the also hold for like sort partitioning, that we can have like that if the iterations are faster, we can have like more iterations, or if the iterations are slower, we should have less iterations. So to summarize, then the impact of this is that for sorting, we have like very cheap arithmetic operations and naturally like very big data transfers in the algorithm, which means that we can tolerate more iterations in our partitioning algorithms, since each iteration is very cheap. On the other hand, in hashing, we have very expensive computation and variable size data transfers. So what we need to do here is to minimize the iterations while maximizing transfer size. And in order to achieve this, we need to share the scratchpad memory between threads, which requires to synchronize between the threads. And this, in the end, leads to like the behavior you saw in the IPC, where the IPC stays relatively low because we have a lot of synchronization between our PIM threads. And so overall, what we can get from this is that sort partitioning fits the UpMem systems a lot better, which is like different from what we expect on like conventional system, where usually like hash partitioning is a lot faster. And there are some previous works that basically claim that on conventional CPUs, that sorting and hashing, or sort and hash partitioning, are equivalent for aggregation, which means that maybe we can also further optimize this on the UpMem system, but it would require like more work on this. So overall, what you can get from this is that because we have like this behavior that we explain here on the UpMem system, now the sort merge join has a higher higher performance on PIM system than hash join, which is a major takeaway of this work, that like most of what we think are the most efficient algorithms on conventional systems are not necessarily the same on PIM system. And one such example is sort merge compared to hash merge join. which also means that we kind of have to reconsider what the state of the art is in terms of algorithm if we want to implement this on a PIM system. So now to the weak scaling analysis. So this is like the weak scaling behavior for the simple operators that don't require data redistribution. And as you can see, the key bottleneck is always the data transfers. And for selection, we have the initial transfers for transferring the data from the host to the PIM system, and the final transfer for transferring the data from the PIM system back to the host. Which for aggregation, on the other side, we only have the transfers to the PIM system that are significant, since after aggregating the data on the PIM system, the size is greatly reduced, which also tells us that aggregation is good if we want to improve like the performance. Like aggregation is good to have in queries if we want to achieve a good performance on PIM. And so sort aggregation is a bit less limited from data transfers, but this is just because the execution time is so much longer and execution is so much less efficient. So, and what we also see is that the asynchronous time, execution basically only improves like the overall end-to-end execution in selection, where we have like these transfers from the host to the PIM system and from the PIM system to the host, because what it does in the end is just overlap these final result transfers and optimize the bandwidth of the final result transfers, which we do not have for aggregation. So now to the weak scaling analysis of the more complex operators, which are the ones that require data redistribution between PIM cores. And we can see first that it's very similar, the performance of the end-to-end performance overall for all three operators, which is because the biggest obstacle in the performance is the data redistribution over PIM cores. So yeah, basically we can basically this means that just optimizing the PIM core code does not really give us as much benefit as improving the data redistribution, as we previously also explained. And from what we can gather now from all the results that we saw on the operator is that the weak scaling behavior is far from optimal. Like ideally, it would just, the execution time would be constant, since we increase like the problem size and the number of processing units together. However, this is only the case for the PIM execution, which you see scales ideally. However, for the data transfer, we start to have contention to different like PIM cores, since they need to share the same memory chunk. So now for the strong scaling analysis, we want to now see how the end-to-end execution time improves by adding more or using more PIM ranks for execution. So we can see that both the transfer and execution time increase with increasing number of PIM ranks. However, it's far from optimal. Like you would expect that if you double the number of PIM cores, that your end-to-end execution time would also be half, which is not the case here. And the reason for this is, again, that bandwidth does not fully scale with the number of PIM cores, since the memory channels from the CPU are shared by the PIM ranks, and we have contention when we add more PIM ranks. The picture is the same for the more complex operators. So overall, we can see that increasing the number of PIM cores is always beneficial for the performance of database operators on the optimum system. And it's always good to use as many cores as available. However, the main bottleneck of these complex operations is still the data redistribution between the different PIM cores, which is our third key takeaway, that current PIM systems are still limited by the weaknesses of processor-centric architectures, which is because processors are still needed in order to perform the data transfers or communication. And this basically reintroduces the main memory bottleneck to PIM architectures. So now we come to the comparison of the database operators to CPU and GPU, like using 8 GB for this, since unfortunately the GPU implementation does not support bigger data sizes. And so what you can see is that the two simpler operations, selection and aggregation, have less overall or negative overall speed up compared to CPU than when we look at the two more complex operators. And the reason for this is the data transfers. Since just transferring the data to a PIM system or to a GPU is similar in complexity to just performing the selection and aggregation. So we cannot expect any speed up there. However, ordering, where we have a lot more memory access during execution, significantly outperforms the CPU on both the PIM and GPU. And we would expect the same for join. However, since data size is pretty small, the PIM execution is not as efficient as CPU, but we'll show later that this is not always the case. However, if we compare PIM to GPU, we see that the GPU is significantly faster than PIM for doing joins, since it just has a single unified memory and does not require data redistribution as we do on the PIMs. So now if we want to compare it a bit more in depth, the performance of PIM to CPU using 32 GB of data size. So here we see that selection basically remains the same. If we compare the end-to-end execution time using all the transfers compared to CPU, we see that PIM is still slower than the CPU. However, if you only look at the execution time on the PIM system, we can see that it's significantly faster than a CPU-based system. For aggregation, the performance gets slightly worse on the PIM system with bigger data size, which is probably because the CPU system can better use this bandwidth. Because this is like because the CPU can better utilize the bandwidth when using many cores if the data is bigger. And now we can see that the two more memory bound or complex operations, like it's operators like sorting and hash join, perform the best on PIM compared to CPU out of all the four database operators, which is reasonable since these are also the more memory bound operators. So the key takeaway that we can get from this is that queries that require ordering and join are better suited to accelerate using PIM system compared to queries that just use selection and aggregation. So now to the results of the TPCH benchmark compared to the CPU. So we can see that we outperform the CPU on the queries 1 to 5 by about 3.9x on average, while we are like slightly slower than the CPU on query 6. And the speed up in queries like 3 to 5 comes mainly from the joins in these queries. They are very join heavy. So as we said before, we can expect these to perform better on the PIM. However, what is surprising that query 1, which does not rely on the on joins, still outperforms the CPU on the PIM system, which is likely because there when we aggregate, we need to aggregate a lot of columns, which leads to a lot of data movement. And what is maybe surprising that we can outperform the CPU even with complex arithmetic operations, like even in the operators that use multiplication, the PIM system outperforms the CPU. And this is because on one hand, we can represent the decimals that are used as 64-bit integers, which is slightly faster than using floating point number. And the multiplication is usually simple since the magnitudes of the numbers multiplied are pretty small, which still is kind of efficient when we do it in software instead of hardware. However, the best performing query on the PIM system is query 4, which does not require any multiplication. So now to the comparison to the GPU. So we see that the PIM system outperforms the GPU in queries 1 and 6, which do not rely on join and thus do not rely on communication, by about 2.2 and 3.3x. And the reason is that, as we mentioned before, also the join requires the data redistribution over the host, which is very slow on the PIM system. However, since the GPU only has unified memory, which is a lot faster to, if it does not require any communication, it can outperform the PIM system when it needs communication. So overall, what we can gather from this is that the TPCH benchmark performance is very limited by main memory. So if we want to improve analytical query processing as it is done it is good to improve or reduce the influence of the main memory bottleneck. And the current issue of the PIM system, or the main issue of the PIM system that we can currently see, is the communication between the different PIM cores. So it's going to be crucial to address this for future generation systems. However, scaling PIM systems should be easier than scaling a GPU memory, since we can scale the PIM system without needing to scale the data buses. So overall, our key takeaway from like all our experiments that we performed is that data analytics is well suited for more data-centric architectures, as the results from PIM show, but also, as you can see from the GPU, which also puts an emphasis on memory by trying to increase the bandwidth. So overall, so now to our conclusion. So memory-centric architectures can significantly accelerate data analytics, as we show with PIMDAL on the UpMem system using this TPCH benchmark. And we find strengths and weaknesses for all our implemented database operators using hardware performance metrics to gather insights into what happens inside the PIM system. And the key limitation of current PIM architecture is that the communication between the PIM cores is very limited, which will be one of the points to address. So overall, we believe that memory-centric system can play a key role in data analytics in the future, especially if they support like even more complex operations that can be used for like more complex data analytics, like machine learning, for example. So now for the end, I want to give a small outlook and have a bit of a discussion on what we need for like truly data-centric architectures. So the first point is already the mentioned communication bottleneck, which, as we saw, current PIM systems are limited by the CPU bandwidth for communication. So we don't really eliminate the memory bottleneck there. So one approach to solving this is just trying to avoid using host main memory by simply transferring the data like from one PIM core to the other directly to the CPU without needing any buffers in memory, which is what one work on the UpMem system proposed. And with this, they already managed to achieve a significant speed up, which could further be improved by using a dedicated hardware unit inside the GPU that is just tasked with doing this sort of like data transfers. Another approach is to propose.
Can I discuss that?
Yeah, of course. Yeah.
So when you say dedicated hardware unit inside the CPU for doing this, I immediately think about DMA.
Yes, like kind of. I'm basically DMA, but for like dedicated to PIM architecture, since one like characteristic of PIM architecture is that they use a different memory layout. So you would need like a DMA unit to specifically for PIM systems.
By layout, do you mean like the data is not split across banks, for example?
Yes.
I see, okay.
Or like split differently across banks.
Yeah, that's true, okay. So can you achieve it by just like introducing new instructions in your ISA?
I mean, you don't need to introduce new instructions. Like this is basically what this work does. Is it uses some SIMD instruction, which can reorder the data in SIMD registers, which then can be like transferred faster to, which then avoids like storing it first in memory and then reordering.
I see. Is it what PID com does?
Yeah.
Okay.
Yeah, like PID com is like the word. They also like they first also implemented like joins on the Upman PIM system, and then they found like the same issue with the data redistribution or communication. So they came up with this approach of speeding up transfer, and then they made like a standalone also paper on this.
Thanks.
So the next are like the other like type of work that deals with this is to use a interconnect network between PIM cores that enables like direct communication between PIM cores without the need to go over the host at all. However, this also creates usually a very complex memory hierarchies where like communication is not very uniform, which is a major drawback of this type of work. So the question here is overall, if we look at how memory is organized today in computer architectures, is like DIMMs that are just connected to a single processor, the optimal DRAM organization, or is there maybe a better way to organize the DRAM in the future for PIM architecture? So does anyone here have like an idea on this?
Okay, I will modify this question a little bit. Why do we even need to connect DIMMs to processors?
I mean, I guess like the main reason is that we want like flexibility with things that we can change. But yeah, the question is like why do we still like rely on one like key connection between a single processor and the DIMM or memory? Like, or I mean, like, do you see that do you think it's realistic that we will go away from like this single bus between one CPU and one memory unit, or will this like stay with us?
So I was trying to bring the discussion to the like those disaggregated memory architectures. So you have all these like CXL nodes, for example, in those kind of systems, right? And your DIMMs are not necessarily connected to processors, actually. It's just a simplistic like CXL controller over there. And then all of them are connected to each other via some sort of network.
Yeah, but is this like the usual setup for like CXL nowadays, or does it still rely on like the CPU for communication or for like data transfers to remote memory?
I guess it's still a processor-centric approach to some extent. But within a CXL node, you don't necessarily need to have like a full-fledged processor, right? You still have that synchronous interface. You have the memory controller on like a separate chip over there.
Is this like the standard implementation of CXL?
I'm not an expert on that, but that's what I understand.
I mean, yeah, we'll get to like this discussion more in depth, but I thought that like CXL is not, I mean, it's not like the standard way of how it's implemented. But yeah, we can also further discuss this in the next slide.
One thing is that specifically for this database application, like as whatever the PIMDAL we are doing in this, the mostly we are, so reordering is one of the problem, like you have to get the data from conventional memory and then transfer it to the PIM memory. But if we just directly have host system, PIM memory and connect it, is it possible like the host will just directly send the request? If you want to read it, you will read it from this PIM enabled memory, send it to host if they want it, otherwise do it inside the PIM system itself. So why do you need, like for these specific operations specifically, why do you need a other memory, the conventional DRAM memory?
I mean, yeah, this is just the current limitation of the UpMem system because, yeah, we need to, we cannot simply address the PIM memory the same way we do the standard memory. So,
But
yeah.
why not? You can just have a host system which reads it from a disk.
Yeah, I mean.
And then just directly write it to the PIM system. Why do we need an intermediate data, DIMs to copy the data?
Yeah, I mean, this could be a further improvement of the work if you use, if you also consider X storage. But yeah, currently the UpMem SDK does not like support this kind of thing. You will need to implement this from scratch, basically. But yeah, currently the UpMem SDK system is really tailored towards like this this type of data movement where you want to move data between other host main memory and PIM main memory. But there are definitely a lot of optimizations that one could do there in the future. So yeah, I mean, storage would be like the next point here. So I mean, since if we have like now especially big data sizes as we have in big data applications, we need to rely on storage to store this data. We cannot just use in-memory databases. So the data movement bottlenecks are even more pronounced when using such storage systems. And the equivalent to processing in memory for storage is in-storage processing, which enables computation inside the storage. And there is some work already that implements like selection using in-storage processing. However, if we want to go further, like looking at the results we now got from PIM, do you think it's feasible to implement like more complex operations using like looking at the results on PIM? Is it feasible to implement more complex operations directly inside the storage, or is this like something that is fundamentally impossible? And yeah, what would you think we need to change inside the storage to support like more complex operations? Yes.
If you look at the smart logistic platform, the well-known implementation is the bandwidth between the FPGA and the flash chips, right? That you need to move the data to the controller and then from there to the FPGA. So I think that first step is to kind of look at increased bandwidth between the compute unit and the flash chips, and the FPGA that off.
So yeah, I mean so I would say the step there would be to I mean, if you want to like use increased performance inside or increased like bandwidth inside the storage, we would need to use in-flash processing. However, do you see it realistically that we can, or do you see how we could like use in-flash processing for doing like these type of operation?
for these sort of operations, we need to perform a comparison operations, right? Like mostly.
I mean,
Comparisons.
for selection,
For
yes.
selection, sorting.
I mean, sorting now already gets like a lot more complicated, right? If we have like, yeah, like separate flash dies, and we have like this communication. So yeah, do you think in current SSD architecture it's feasible to do like sorting using in-flash process?
The problem will be for storing the intermediate data, right? So you need to write to the SSD a lot of time to do these sort of operations, which is much worse for an NAND flash based.
Yeah, I mean, so this also seems to me like one of the major issues. I don't know if there is a way to address.
What is the intermediate data and sort?
Like you need to partition the data, then you need to reorder it, right? So where will you do those sort of operations?
Yeah, aggregation is different.
Not only aggregation, right? In the sorting operation, when he explained like you need to create the partitions, then you need to reorder that using some optimizations. Where will you store the intermediate data? As a using only in flash processing may be difficult. But also for in-storage processing, like for these sort of workloads, they will have a lot of redundant, redundant reads going to the same database or maybe updates to the database, which will be much more complicated. Whereas in the PIM system, as you have DRAM, so DRAM reads are faster and writes are faster. So it will be good to fetch it once, then do things in your DRAM as a PIM system or a POM system. And then once you are done, let's say you want to update after some interval, you can update your database that's in your storage. So is in storage really good for these things?
Yeah, I mean, that's kind of the question I'm trying to answer.
I would say,
I mean, to me, it seems like there are some fundamental limitations.
yeah, with respect to the workload, right? Because if you have some update based workload, you want to update so frequently your database, then in storage or something related to storage is not feasible. Right?
Yeah, but also, as you said, for like sorting, it seems unfeasible if you need to.
But in flash, I would say in flash. I will now come to in storage. Let's say if you have a smart SSD kind of system also, where you have you need to read a lot of times from your SSDs, right? NAND flash. And NAND flash reads are much slower than your DRAM reads. So if you have to, but that DRAM in the storage is a bit smaller than the post DRAM. Depends on the application you can.
So how many data elements, or basically how much data you need to sort actively?
I mean, there are like benchmarks on sorting that are like terabyte or like.
No. Sorting in general, I understand, but for a specific application that you're putting.
Yeah, I mean, it's definitely less than what you have for. You use it definitely less than the other operators, so it's the least commonly used. But I mean, the same goes for join. Like there, you also potentially will need to like partition data and write it. So yeah, there we will also, it's maybe a bit better suited for in storage computation than sorting, but yeah, we would still need to address like challenges like writing.
Is sorting in the middle of operations or the beginning or in the end?
In the end, usually.
Okay. So why do we need to do? We can do it outside the storage, no?
Usually, yes. I mean, so this is like then the question here that if we cannot do these more complex operations inside the storage, maybe we need a different approach where we perform some of the operations in the storage and some of them outside.
Mm-hmm.
Which is basically the next question. So if we assume we cannot do this all the operations like in storage or all the operations in PIM, what would the ideal computer architecture for data analytics look like? So do you have any ideas on this, or maybe we can go like to the next talking point, where maybe it gets also a bit more clear? So the final point is about system organization, which we kind of already teased a bit before. So assume like the ideal computer architecture consists of many different specialized units that can perform like one task very well. So in this case, should we still rely on a central unit to coordinate data flow like a CPU, or should we try to move away from this and develop a more sophisticated distributed mechanism? So what do you think is like the CPU as a central processing unit gonna be still relevant, or do we need to think about something more advanced?
I mean, I guess it's workflow dependent. Like also what you showed in your analysis, like some workflows are like embarrassingly parallel, right? So they're really well suited to acceleration, let's say, moving operations near the data. But I think currently, like when we have resource contention, like we need to wait for some operation, things like that. Also from the algorithmic point of view, like I would say like the parallel algorithms and things like that, we haven't fully developed this yet to make things parallel and performant enough to beat the simple CPU.
The question is then, as you said that we like some workloads could be like probably better for like these type of systems, but do we still need, or then the question becomes, how do we coordinate between these units? Like, do we try a more centralized approach, or do we try a more decentralized approach? So one example of this that it currently exists is that in NVIDIA GPU direct storage, we can have PCIe switches that enable like direct transfers between storage and GPUs without needing to go through the host. However, like this, we cannot directly integrate the DRAM into this the way it's currently implemented, because one reason is that we have memory controllers integrated into the CPU to access like DRAM. And the other point is that addressing happens through virtual memory using the operating system, which also requires the CPU to as an intermediate like translator. So do you think there is a way to efficiently integrate like DRAM or PIM without like losing the benefits of this current processor-centric design with virtual memory? I mean, I guess this is like what you said before, that about CXL, but I don't think like CXL really like solves this currently.
I actually don't like to be limiting this kind of research with like some certain product.
Yeah, no.
I mean, when I mentioned CXL, I mentioned the concept of like aggregated memory in more general. Like it can be implemented in different ways as well.
I'm just like thinking about if And currently, I don't think it's like really disaggregated. Even with CXL, you still have like the CPU that you use, especially like for virtual memory. And like, do you see a way that we can like still keep virtual memory or virtual addressing and while having like disaggregated memory, or not a CPU that manages it?
I'm close to this.
I mean, this may be also a question for like, people working on virtual memory. Like, do you think virtual memory has a future in like disaggregated memory system?
I don't understand what's the problem with virtual memory.
So, I mean, currently you need like the CPU or the OS that manages this virtual memory. But if
Yeah.
you have like now multiple PIM systems that like collaborate together, would you still like need a CPU to like perform this address translation? Or what is then a different way to do address translation?
Sorry, talking about like put an accelerator for address translation or something like that.
I mean, that's a question. Like, will we need dedicated address translation units, and is this a better design than using CPUs?
This already happens in the previous address translation on device. So the question is how will this be implemented and whether or not this is needed in this sort of scenarios. Do we need this isolation? Do we need multi-tenancy in the modules? And if we need to support virtual memory in order to have all these security guarantees. Right? But if we don't, and we don't have multi-tenancy, then possibly we could completely migrate and not. This would be.
Yeah, I mean, so the first question is, do we still need virtual memory? Like, can we just completely get rid of it? Which maybe seems difficult. And if like not, then what is the alternative to the current use case? So how does address translation happen on the GPU?
How's virtual memory helping GPU?
No, like you said, that GPUs perform like address translation.
Yes, if you have a way inside the GPU to perform address translation.
So does the GPU also use virtual memory? Or?
Yes, for programmability, right? Something that otherwise the programmer will need to work with physical address. Also in multi-tenant scenarios, this is very difficult when it comes to security. This is very dangerous when it comes to security because if you have more than one people working or executing on the same device at the same time, you need a way to differentiate. You cannot give access to the entire memory for security benefit. So if your module wants to support multi-tenancy, virtual memory would have to be implemented to understand, or at least this isolation between the two.
But this is only for the GPU memory, right? So like inside the GPU.
No, you can have both. You can actually write programs in unified virtual memory that sees both system memory and GPU memory as a one memory space.
So then do you have like two different, like on the CPU and on the GPU, like different memory spaces, or is there a way to coordinate between GPU and
There is a way to coordinate. It can be tricky how you do it as overhead.
So yeah, then the question becomes like, is this applicable to also like PIM systems or like more, or even like if you also use like storage system? Is this approach scalable if you want to have like a full, full system with many different accelerators.
It's not necessarily scalable, and it is, and it could be, it could even not be performant. But the real problem is whether or not we need it, and what's the system that we're using. If we can define the system that we're using and what are the needs for this system, then we can make the choice on whether or not we should support it and whether or not we should have this additional overhead to offer the programmability, flexibility, and security guarantees that we need.
Yeah, I mean, I guess if you want, I mean, like, let's say the system where we will need this the most is probably like some virtualization based so cloud infrastructure where you like try to run like the different applications from like different people. And for example, for databases, or a lot of these applications also use databases. So it seems like there could be a use case for this.
So if we're talking about cloud applications where you do need to essentially perform different operations for different users, then for sure you need this support. If you're talking about databases, for example, that I could have an isolated device that only I am using, then possibly it could disable you completely.
So yeah, I mean, then.
So what I'm saying is that it is a trade. Both approaches could be used.
It also depends on how much programmable you want. If you want to ease programmer effort, and you want to support virtual memory, irrespective of what you can install.
This is more difficult to quantify.
It is very difficult to quantify, I agree.
So I can definitely see that if in like cloud application, you would want to add like more specialized accelerators, like processing in memory or GPUs. Like if you talk about like this ideal computer architectures, how it looks like, I think it could also be like the general architecture we use in cloud has a lot of specialized units. And then, yeah, the question becomes, do our current like mechanisms, are they enough for this, or will we definitely need something new?
It really depends on how much you offload to each of these devices. If you have large granularities of what you want to offload, then you can have independent support. If multi-tenancy is another problem, then you definitely need virtual memory.
It usually works like I have seen many works that essentially introduce new devices, and they put in these devices specialized memory management units that can translate in larger granularities or depending on what the application is. Also, we can look at this from a different perspective, from the perspective of adaptation. So if we want to have ease of adaptation for this sort of devices, then we should use something like virtual memory that eases programmability and essentially makes these systems easier to be integrated into the current time.
I mean, I guess we will find out like what the ideal computer architecture will look like in the future. But yeah, I hope that the PIM or maybe also this work is like one step towards this architecture. And yeah, otherwise, I think if there are no other questions, that's it.
Close. If you have final remarks, I can stop after that.
Okay. Thank you, Manos, for your presentation and great work. Thanks for the discussion. We will meet again next week with 2 more very exciting presentations
On Tuesday.
On Tuesday. Yes.
on Tuesday. So see you next week. It's
You didn't ask them to